In section 5.1, we talked about the dot product on vectors in Rn, and now we're going to take that idea and generalize it to all sorts of weird vector spaces with something called an inner product. So an inner product is a generalized dot product. It is a way to multiply two vectors and get a number. Now, because we want to distinguish it from the dot product that we've already seen, we don't want to use the exact same dot product notation, so we're going to use a different notation now. So what we're going to do is we're going to write these bracket symbols here. And what this means is the inner product of x and y. So before, we would call it x dot y, and now we're going to call it bracket x and y. They mean the same thing, at least for the normal Rn. What we're going to see is we can come up with an inner product for all sorts of crazy vector spaces where you don't have a normal dot product. Now the thing is, we have an official definition for what properties this thing has to hold. So here it is. This is the definition. A function that we're going to call it bracket. It's going to go from v cross v to r. So it's going from two vector space vectors to the r here. Is called an inner product if it satisfies the following four conditions. The first is that if you do an inner product of x and y, you always get the same answer as if you did an inner product of y and x. So cross product is not commutative, but this dot product version is commutative. So it has to be this in order to be an inner product. Second thing is if you were adding two vectors inside a dot product, you can break up the dot product into two separate results based on the two separate vectors. So this is called linear, right? Because you're adding inside means you can add outside. That's the linear property. Third is if you have a constant inside the dot product, you can factor that out of the dot product, and really that's the second linearity property that we would need. And the last one, this one's maybe a little weird at first. It says if you take the dot product of something with itself, the answer is always going to be greater than or equal to 0, and furthermore, that if the dot product is equal to 0, the only time that ever happens is for the 0 vector. Now the reason why we have this one, number 4, is because we are going to take x with x, and we're going to think of this as the length of x squared, right? Remember that notation we had before? That's what it's going to be. And so in order for this to be true, in order for it to be the square of a number, it has to be greater than or equal to 0. That gives us the first part. And in order for it to be equal to 0, the only time you have a length of a vector giving you the answer 0 is if you have the 0 vector. So that's where that comes from here. And so we could check that the normal dot product satisfies all four conditions. It's a little tedious here, so I'll say proof left to the viewer. All right, I'll let you guys do that work if you want to. But this is the definition. This is the idea of what an inner product is. And so what we're going to do now is we're going to then look into some weird vector spaces and look at examples of inner products on those spaces.